This is how the James Webb Space Telescope looks deeply into the universe. It takes in radiation that has traveled for more than 13 billion years. As the universe has continued to expand, ancient radiation has stretched concurrently. When we pay close attention, we are essentially gazing into remote star systems, looking almost back in time to the precise instant of the Big Bang. Though the universe seems infinite in scale, every segment of it originated from what is commonly termed the singularity. This notion presently underlies our grasp of the Big Bang model. Despite this, the JWST, or James Webb Space Telescope, has unveiled extraordinary revelations about the beginning and development of the universe, rendering even veteran researchers amazed. Renowned physicist Brian Cox has stated that the novel insights provided by the JWST may fundamentally reshape our perception of the universe as a unified whole. Come along with us as we investigate this information that may alter our comprehension. In honor of the former NASA administrator James E. Webb, the JWST is a modern-day success story. It represents astrophysical engineering at its finest, a significant technological advance compared to its predecessor, the Hubble Space Telescope. Developed in collaboration with NASA, the European Space Agency, and the Canadian Space Agency, the JWST incorporates innovations from avant-garde engineering and a specialized architecture designed to capture the universe with extraordinary fidelity. Unlike the Hubble, the JWST provides crisp, high-resolution visuals of distant astronomical objects primarily in the infrared spectrum. This distinctive ability allows it to penetrate cosmic dust clouds and reveal celestial events that were previously hidden. The enormous 6.5 meters primary mirror, consisting of 18 hexagonal parts, is significantly larger than Hubble's mirror. Situated around 1.5 million kilometers from our planet at the second Lagrange point L2, the observatory orbits the Sun in sync with Earth, offering a steady and uninterrupted view of the cosmos. Gazing into distant parts of the universe is not simply a question of distance, it's a mode of traveling through time. The JWST's thermal tools make it possible for researchers to observe events and astronomical bodies that originated several billion years ago. As the universe expands, the radiation from these ancient sources becomes redshifted, shifting from visible wavelengths toward the longer infrared spectrum. Thankfully, the JWST was designed to detect this radiation, enabling researchers to investigate star formation, study the evolution of galaxies, and examine the environments of exoplanets. One of the most remarkable recent revelations includes identifying a colossal collection of star systems at the far edge of the observable universe. This defies long-standing assumptions about the creation of the universe and prompts researchers to reevaluate fundamental cosmological principles. To recognize how we reached this scientific milestone, it's helpful to trace the history of astrophysics. Ancient societies, such as the Chinese and Greeks, laid the groundwork by observing planetary movement. The 17th century saw Newton's laws provide a theoretical framework for understanding celestial forces and gravitational mechanics. At the start of the 20th century, astronomer Edwin Hubble produced transformative breakthroughs. His observations demonstrated that distant nebulae were actually star systems beyond our own Milky Way, revolutionizing our comprehension of the size and motion of the universe. Hubble's law, showing that distant galaxies are receding at faster rates, offered powerful proof of the universe's expansion. The space race following World War II commenced with Sputnik's launch in 1957. This was followed by Yuri Gagarin's historic orbit in 1961 and the Apollo 11 moon landing in 1969, monumental feats in outer space exploration. The launch of the Hubble Space Telescope (HST) in 1990 ushered in a new era, providing unmatched images and perspectives on the universe. The progression from ancient sky gazing to the technological powerhouse represented by the JWST shows a never-ending quest for cosmic insight. The HST captured emblematic images, such as the Pillars of Creation and the Eagle Nebula, revealing stellar nurseries amid massive dust and gas clouds. Its deep field image revealed thousands of galaxies in a region of space that once seemed empty. The HST also analyzed exoplanet atmospheres, detecting organic molecules and water compounds, pointing to the possibility of life beyond our planet. By studying the SN 1987A supernova, it helped decode the life cycle of massive stars. These achievements established the telescope's legacy in astronomy. Its successor, the JWST, was engineered to push those limits even further, especially in exploring the origin of the cosmos thought to have begun around 13.8 billion years ago. The current model argues that the universe began as an extremely hot, dense singularity that rapidly expanded. As it grew, matter, energy, and fundamental forces emerged, with gradual cooling resulting in the formation of atoms, stars, galaxies, and the large-scale structures we observe today. The Big Bang model also accounts for radiation from the cosmic microwave background, proportions, elemental and immense cosmic architecture. Despite being accepted, the model faced initial skepticism. Theories other than the steady-state proposal called for an infinite universe with no beginning. Concerns regarding the singularity, expansion, and some oddities were common. Over time, the majority of objections were resolved, especially following the 1965 detection of radiation from the CMB that strongly supported the Big Bang predictions. Missions that followed, such as COBE and WMAP, delivered more precise measurements, supporting the model with extraordinary accuracy. Enter the JWST, equipped with cutting-edge thermal instruments that can penetrate cosmic dust and allow scientists to observe the earliest radiation in existence. Due to its strengths, it can target star-forming regions, investigate stellar nurseries, and pinpoint stars that Hubble and other optical observatories could never recognize. Heat radiation, with its longer wavelengths, penetrates dust from other galaxies, revealing hidden aspects of space and time. The JWST also excels at examining cooler astronomical objects, including brown dwarfs, distant star systems, and potentially habitable exoplanets. As star systems disintegrate, their radiation changes color. These signals are detected by JWST's thermal sensors, offering insight into the cosmos's earliest chapters. Cataclysmic phenomena like black hole mergers and star births frequently release energy in thermal frequencies. Therefore, the JWST not only enhances optical observations but surpasses them, illuminating previously unreachable facets of the cosmos. Recently, it discovered a truly stunning find. Massive structures in the galaxy only a few 100 million years after the initial event. The very first star systems, visible at the dawn of the universe, appeared more massive and mature than our models predicted. This suggests that the beginning of the universe may have transpired faster and more turbulently than anticipated. Such findings are transformative. They challenge existing paradigms and hint at mysterious physical conditions or processes in the early cosmos. The findings of the JWST are causing cosmologists to reconsider or refine their models, especially concerning the creation of structures and galactic evolution. The expansion and abundance of these early star systems also alter expectations. Numerous systems exhibit complex and inconsistent characteristics compared with the idea of growing slowly and steadily. We may instead be witnessing rapid, large-scale changes that point to a cosmic web denser and more intricate than previously thought. The gap between data and theory has sparked vigorous disagreement among researchers. How did such massive structures form so quickly without compromising the fundamental principles of physics? Could unknown mechanisms or unseen phenomena be involved? The answer may lie in further scrutiny and investigation. In astrophysics, surprises often emerge from observations. Spectroscopy examining radiation to determine the characteristics of celestial objects plays an important role. It demonstrates composition, density, temperature, and movement, giving us a thorough understanding of how galaxies and stellar bodies mature. Already, JWST has demonstrated that early interpretations can change. Whereas past studies suggested simple star systems dominated by hydrogen and helium, spectroscopic examinations now reveal heavier substances and unforeseen compounds in the early cosmos. This challenges assumptions about chemistry and the dispersion of materials. Parallel patterns of development emerge in galaxies. Once assumed to follow a uniform path, additional information now reveals complexity and diversity, pointing to a much more varied primordial cosmos than previously envisioned. Lastly, one of the most exciting features of JWST is its ability to investigate exoplanet atmospheres in depth. By examining the filtered radiation of these planets' skies, the observatory can identify crucial chemicals such as methane, water vapor, carbon dioxide, and organic molecules, every possible characteristic of life. Moreover, the JWST is revolutionizing our insights into stellar creation. It can see through gas and dust to observe new stellar bodies emerging, offering clearer comprehension of how systems such as our solar system originated. This helps us piece together the journey from cosmic dust to worlds capable of sustaining life.